So our next speaker is Emiel, and he will tell us more about PyRA, a PyCalculus for verifying protocol that use remote attestation.
Okay, so hello. As Katalin said, I'm Emiel, and I'm presenting joint work with Matteo Busi, the previous speaker, and Dominique Devriese. We are presenting the PyRA, as already said by Katalin. Okay, so first a motivation, specifically a motivation for remote attestation. So what do we want to achieve with this? Well, suppose a setting where we have a trusted component B, and it wants to communicate with an untrusted machine A, an untrusted machine, and specifically it wants to communicate with a component A on that machine. But the untrusted machine can change A however it wants when A is deployed on the untrusted machine. So to build up trust in the component A on the untrusted machine, remote attestation gives you tools to encapsulate the program and build up trust in the component, so you're sure you're actually communicating with a component A and not some changed component. Okay, so that's the motivation for remote attestation, and there have been several hardware implementations such as Intel SGX, MIT Sanctum, Soundquiz, and TPM. And the problem is these are all different implementations, and our goal is to look at it at a high level at RA. And we specifically try to ignore everything that is different between these things. So the implementation of how they implement array, how they do their isolation primitives, how they do their communication primitives. And to do this, we make a variant of the PyCalculus that supports remote attestation. And we will subsequently show like its use by proving the security of a protocol that uses PyRA, like the proof uses PyRA. Okay, so to explain PyRA, I will first explain how we look at remote attestation. So again, A wants to show that it's actually running the code of A to B. So what A is going to do is it's going to ask the root of trust, which is most of the time like something embedded in the hardware, to check the code of A and sign a token that promises, okay, the code of A is actually running there. And this is called an attest. And A is going to send this attest of its identity to B. B can then check this thing. This is most of the time, this will be a test of the hash of the code of A. And B can sign this. Okay. I realize I have a pointer. So B can then check that the attest actually contains the code of A, and then B can trust that A is actually the code of A. Okay. The second ingredient we need to build up the PyRA is the PyCalculus. And specifically, I want to highlight three constructs: the send construct, the receive construct, and the parallel composition construct. So what it is if you've got a send construct and a receive construct in parallel, then you can rewrite it by sending from the one process to the other process. So in this case, 42 is sent over here. That means Y is replaced by 42. And then we print 42, which means it appears on the trace. Okay, so this is the PyCalculus, but we want to change some stuff about this to model the ideas of remote attestation. The first and most important idea is this idea that the root of trust first reads the code of A to make sure that it's actually correct, and only then generates a token. And that we do this with the getAttest construct. And so how it works is getAttest is the X is just a variable and P is a process. And this will evaluate to P where the variable X is replaced by the attest of P, but specifically the attest of P. So this means that no other program than P can get access to the attest of P, because you need to get attest command to get access to the attest. Okay, so now we have this attest and we want to use it in communication. So we put a program Q in parallel, And this program Q, we will elaborate it to a receiver. Again, to have like a rat thread through this presentation, we will try to send 42, but this time in a like authenticated way. So Q is a program, and it receives a message, but in a authenticated way, which means we still have the variable by which the message will be replaced. But now we also have a field where Q can demand, I only want messages from senders who can show me the attest of P. And well, it wants to stay anonymous, so it doesn't want to show its own attest. Then we also need to elaborate Q. Q becomes the sender who sends 42, and it will present its attest, but its attest is X, which is then replaced by the actual attest, because we have this substitution here. And now the communication can go through, because the attest that is expected by the receiver is actually the attest that is presented by the sender. So this means that, well, again, the Y is replaced by 42, and then 42 is printed, so 42 will again appear on the trace. The interesting thing here, compared to the PyCalculus example I showed you, is that if you put an attacker into the game over here, this print statement will only print 42. Because if you put another attacker in there, the only way he can get access to an attest of P is because it is P. So the only communication that will work is sending 42. Okay, so this is the idea of PyRA, and now we want to show its use by proving the security of the MAGE protocol. And specifically, the MAGE protocol is a solution for mutual authentication. But first, what is the problem with mutual authentication? Well, just as before, A can send its test, B can check its code, but then now we want A to also build up trust in the code of B. So B sends back its attest, and A checks the code of B. But now there's a problem, because the code of B, to write it, you need to know what the code of A is. And to write the code of A, you need to know what the code of B is. So this is a circularity problem, and well, you can't write it like this. However, there is a solution. It has some drawbacks, but there is a solution highlighted in the MAGE paper, which was published at Usenix in 2022. And the idea is to have a pre-processing stage to bootstrap this circularity. Specifically, what they do is they compile this table of identities, and specifically, so for each program in the so for each entity for which you would want to do mutual authentication, you need to know this beforehand, and you all compile them into a table where it says, okay, this is the name of the program, and we have the hash, not of the whole program, but of everything except its reference to the identity table itself. And then once this pre-compiled identity table is compiled, we just concatenate it at the end. And then we don't just send an attest of the code of A, but a attest of the code of A concatenated with this table of identity, which is the same for each of these components. So this means that B can check it by just looking for its 8th entry of its own identity table and attaching the identity table to this. And then the same the other way around. So now circularity is broken because well, this refers to the identity table, and this then refers to the code of A without the identity table, but because it doesn't refer back to the identity table, circularity is all right. Okay, so this is the idea of MAGE, and now we want to show the security of this, but there is one important caveat we noticed when we tried to show the security, is that there's no way to distinguish whether you're talking to distinguish exact copies. So for example, there's no way to know whether A and B are talking to the same C or to some different, some like exactly the same type of C, but no, not the same process. Of course, there is ways to do this, but there's no non-trivial way. It would be like you would have to have like lookup tables with public keys or something like that, and that hasn't been mentioned in the MAGE paper at all. Okay, so we want to prove the security of MAGE, and we want to use PyRA to do it. And specifically, how we'll show the security of MAGE is we will make a source language, and we will make a compiler. So we'll make a source language where mutual authentication is just built in. You don't have to think about it; it just works. And then we will make a compiler which will use the core principles of MAGE, so specifically this pre-processing stage, to compile it down to PyRA, which is a system that supports remote attestation. And we show that this compiler is secure. So specifically, what do we mean by secure compilation? We have two secure compilation criteria, which we looked at. We looked at fully abstract compilation, which means preservation of contextual equivalence. So this means if two programs can distinguish, some attacker can distinguish two programs in the source, then when you compile them down, the compiled programs can also be distinguished, and vice versa. If they can't be distinguished, then they can also not be distinguished in their compiled versions. The other secure compilation criterion we looked at is robust relational hyperproperty characterization, which says that if we have a context, there exists a context in the target, there is a context in the source that can emulate its behavior, basically. That means that if we have just a program and we look at the compiled version linked with the context, then we can recreate that behavior by linking the source context with the program. So this means that if the compiled program would have a leak somewhere, we can recreate this leak in the source as well. So this means that the compiled version is at least as safe as the source version is. Okay, so this is our secure compilation criteria. Now we want to look at the source language we use to compile from. And this is a language we call PyActor because it uses actors, specifically these boxes. They are actors with name n, or name m, and then a program in there. And the communication primitives are also changed again. And they say, okay, I want to send from, I want the message, the receive says, I want a message from M, and it needs to come to myself. So I'm prepared to say my own identity. And in the send, it comes from myself, and I want to send it to N. So let's start by replacing the selves by the names of the programs. And then we see that we have the same signature. So this is a mutually authenticated communication because they both say where they both want to only send to attacker M or N in this case. Okay, so because these signatures match up, we can send 42 again, and then we can print 42 again. Just like in the PyRA case, it's interesting to mention that because there is an implicit trust in the source language that you can't just add another actor with the name M, but some other program. So you know that if you get a message from actor M, it's actually 42 again, because the program will be this program. And because copy attacks are possible, the attacker can just add copies in there, which, well, in this example are not really relevant, but they might be relevant in more complicated examples. Okay, so this is our source language. We have our source language. We have our target language. Now we want to discuss the compiler. But the problem is we have this pre-processing stage, so we can't just specify the compiler. We first specify what I called a pre-compiler, where we basically, it's the compiler, but it is parametric in the table of identities you'll be using. So this means that we can then use these pre-compiled programs to compile this table of identities. And then we have the actual compiler. So the interesting things here are like, this is just to show how most of the constructs in the compiler are. The actor becomes an attested region. And specifically, so the variable y is the variable that will be replaced by the attest. And we also keep in mind during the compilation what the last variable was that the attest will be replaced by. So okay, so in this case, get attest would then be the compiled program with IDT and the attest. And then we can see this in the communication, where we have communication from itself. So that means that it has to present its own attest, which it does over here. It also wants to receive from someone else, and there we need the specific MAGE things. So it's the attest it expects from the other party will be the ID'd entry of the identities table with a concatenated with the whole identities table. Okay, so this is our pre-compiler, and then we use this to compile the table of identities. So specifically, this means if we look at a program, we just, so for example, here we have 2 actors and just 1 other program. We discard all the non-actors. We only look at the actor content. And then, oh, excuse me, I pressed the wrong button. Okay. And then for the actors themselves, what we do is for every name, so we get a dictionary with the name of the actor and the precompiled process where the identities table we use is just a fresh variable. So this is then the table of identities. And then we just define the compiler by plugging the result of compiling this table of identities into our pre-compiler, and we get our compilers. Okay, so we have our source language, we have our target language, we have our compiler, which uses the ideas of MAGE, the pre-compilation stage and the extending of the hash table. And then the only thing that's left to do is show that this compiler is actually secure. And I told you about these secure compilation criteria we proved, namely fully abstract compilation and robust relational hyperproperty characterization. But in reality, we didn't do that. We showed a weaker version. Specifically, we only show, for example, full abstraction for pairs where the actors in the program are the same. But there's a good reason for that, because actors in the target can always be distinguished because they freely give their identity in the form of an attest. So it wouldn't be logical if we would be able to prove this. But what this proof does tell us is that the clients of actors, so the people that depend on the services actors deliver, they will stay safe. So yeah, and that's in the end what we actually want from this kind of protocol. Okay, so this is the secure compilation version, the fully abstract compilation version, and this is the RHC version, where instead of, so formally, before the source context, which emulates the target context, didn't depend on the source program we were looking at all, but now it depends on the, specifically on the table of identities of this program. So that's what we do by universally quantifying over the table of identities and then only allowing programs with the right table of identities, as I highlighted over here. So we made a compiler, so we made a target language, and then we showed its efficacy by making a source language which has the promises of the MAGE protocol. We made a compiler that uses the intrinsic ideas of the MAGE protocol. We showed this compiler secure, and this is a proof of the security of the MAGE protocol. So are there any questions or suggestions? I'm happy to answer them.
Yeah, so we have time for a couple of questions.
Okay, so super nice presentation. I guess a very basic question. I mean, you built all this for proving the security of the MAGE protocol. Do you think this can be used also with other remote attestation protocols, or would require like changing completely the framework?
We hope so. There's one thing that we did for like quality of life, which might need to be changed to be more general, and that's we have these authenticated communication things here, which we added in because we didn't want to worry about replay attacks and man-in-the-middle attacks and all those kinds of things. But there are like more low-level primitives which we didn't opt for, but do specify in the paper how they would work, which you might need to add in. But I would advocate for not erasing this and adding in the other thing, but just giving you both, so you still have the ability to not have to think about replay attacks and things like that. And the construct is just you can encapsulate your attest with a message such that you can't get the attest out.
Okay, so maybe following up on this, sorry. So for instance, if you were to add this kind of low-level primitives, would now your language get closer to like other protocol verification languages? I
don't know.
I mean, I'm just trying to.
So we did like so these are quite high-level constructs, but I call them the package function. These I looked at some like actual implementations of RA, and they show up everywhere in one form or the other. Yeah.
Okay.
Good talk. So proving full abstraction is really, really, really difficult. And it looks like the security properties which you're interested in are things like, you know, if somebody believes an attestation is true, then in fact that attestation happens. So attestations don't come from nowhere. And that has a lot of the same flavor as something like correspondence assertions. And
sorry, can you repeat the word?
So correspondence assertions.
Okay.
And correspondence assertions so preservation of correspondence assertions is much, much easier to prove. So I was wondering, are there examples where you actually want like the whole thing of full abstraction rather than something much simpler like preserving security properties?
I don't know. I don't know. I did already prove it, so
I've done all the hard work.
I hope there's the good use for it. But,
Okay, so we have time for one more question if someone would like to ask. If not, let's thank the speaker again.